Previously, we have looked at factor theorem, fundamental theorem of algebra, conjugate root theorem, and irrational root theorem. Now we will look at Descartes' rule of signs. Now, wouldn't it be great if we could predict the nature of the roots before trying to find them? That would be really nice. So, that is where Descartes' rule of signs comes. It says, for the polynomial f sub n of x with real coefficients, the number of positive real roots is a number of sign changes or less by an even number. We'll understand this with some examples. And it also says for the polynomial f sub n of minus x with real coefficients, the number of negative real roots is the number of sign changes or less by an even number. Descartes' rule of signs gives only the possible number of positive and negative real roots. It does not determine their exact values. When applying Descartes' rule of signs, sign changes are counted between consecutive non-zero coefficients. So let's look at some examples. We have f sub 4 of x equal to x to the power of 4 minus 10x cubed plus 35x square minus 50x plus 24 equal to 0. Let's apply Descartes' rule of signs. The signs that we have is first term has plus, if nothing is there, plus, then minus, then plus, then minus, and then finally plus. Now we count the change in sign. So plus, minus, there is a change. Minus, plus, there is a change. Plus, minus, there is a change. And minus, plus, there is a change. So how many changes are there? 1, 2, 3, 4. 4 changes are there. Since there are 4 sign changes, the number of positive real roots is the number of sign changes or less by an even number. So 4 positive real roots or less by 2, that is 2, or again less by 2, 0. So the number of positive real roots can be 4, 2, or 0. So these are the possibilities. Now what we do is we take this equation and replace x with minus x. So f sub 4 of minus x is equal to minus x to the power of 4 minus 10 times minus x cube plus 35 times minus x square minus 50 times minus x plus 24 equal to 0. Here actually equal to 0 is not required because there are no sign changes possible. Okay. So now simplifying this, we get f sub 4 of minus x is equal to x to the power of 4. Here cube will give us minus x cube. That minus times minus is plus. Similarly here minus will disappear because of the square. So all the terms become positive. So that means there are no sign changes in f sub n of minus x, which means there are no negative real roots. So what do we know now? We know that positive real roots can be 4, 2, or 0, and there are no negative real roots. So which means if there are 4 real roots, then done. But if there are 2 real positive roots, then what happens? There are still 2 remaining. They will be complex conjugates or non-real complex conjugates. If it is 0, then you will have 2 pairs of non-real complex conjugates. Actually, this, if we write it in a table form, it becomes much more clear. So these are the possibilities. total roots, fundamental theorem of algebra says if it is a degree 4 equation, then there will be 4 total roots, out of which if 4 are positive real roots, that means negative roots and non-real complex roots will be 0. But if positive real roots is 2, negative is 0, that means 2 will be complex, non-real complex roots. And if there are 0 positive real roots, then there will be 4 non-real complex roots. Now here, this notation C \R, it means complex numbers excluding real numbers. Remember, all real numbers can be written as a plus 0i. So that means all real numbers are complex numbers. So to explicitly specify that we are talking of non-real complex roots, we can use this notation. So that was our first example of applying Descartes' rule of signs to figure out the nature of roots. Now let's look at the second example. Now the second example is the same thing except the signs have changed. So x to the power of 4 plus 10x cubed plus 35x squared plus 50x plus 24 equal to 0. Now here, since all the coefficients are positive, there are no sign changes. Therefore, there are no positive real roots. Now, let's take f sub 4 of minus x. Applying that, we get x to the power of 4 minus 10x cubed plus 35x squared minus 50x plus 24 equal to 0. Now here there are 4 sign changes. 1, 2, 3, 4. Therefore, the number of negative real roots can be 4, 2 or 0. So again, creating a table, we get 3 possibilities. 4 negative real roots, done. But if there are only 2 negative real roots, then 2 will be complex conjugates. And if there are 0 negative real roots, then there will be 2 pairs of complex conjugates. Let's look at the third example. Now here we have x to the power of 4 plus 4x cubed minus 7x squared minus 22x plus 24 equal to 0. There is no sign change here. 1, no change. 2. So there are 2 sign changes. Therefore, the number of positive real roots can be 2 or 0. Let's take f sub 4 of minus x, which gives us x to the power of 4 minus 4x cubed minus 7x squared plus 22x plus 24 equal to 0. Now, let's look at the sign changes. 1, 2, again 2 sign changes. So there are 2 sign changes. Therefore, the number of negative real roots can be 2 or 0. Now, let's look at the possibilities. Total roots are 4. Positive real roots, if it is 2, then 2 negative real roots. If 0 positive real roots, then 2 negative real roots, which means 2 are remaining, they will be the complex conjugates. Now, if again 2 positive real roots and 0 negative real roots, then 2 will be complex conjugates. Now, if positive real roots are 0, negative real roots are 0, that means 4 complex roots, non-real complex roots, or in other words, 2 pairs of non-real complex conjugates. Interesting, right? Now, the starting point in applying Descartes' rule of signs is to realize that the total number of roots is equal to the degree of the polynomial by the fundamental theorem of algebra. So, you already know how many roots are going to be there. The number of non-real complex roots is always either 0 or an even number. because they occur in conjugate pairs by the conjugate root theorem. So now it shouldn't matter whether we get a fourth degree polynomial equation or a 10 degree polynomial equation. We just apply these rules and we get the nature of the roots. Now, one very interesting fact is a lot of algebra came about in the pursuit of the roots of polynomial equations. So we are going to look at lot of algebra based on roots. That's it for now.